The other one that took this a little bit further to new domains is CNN features off the shelf. So you're going to use CNN features without any fine tuning, and it's going to give you a baseline. So previously in computer vision, you would take an image, you would do some part annotation, strong DPN, learn normalized pose, extract features, gradients, LBM, etc., LBP, etc. And then at the end, you do your support vector machine. So there was a lot of hand engineering going on here. Now, the idea is that you can bypass the entire thing within CNN, and you can apply it to different domains. You can do object classification. And from left to right, we are going further and further away from the original task that the network was trained on. So these CNN features are being trained on ImageNet, which was the object classification task. Now you can do object classification, scene classification, bird subcategory, flower recognition, human attribute detection, object attribute detection, Paris buildings retrieval, Oxford buildings retrieval, sculptures, scene image retrieval, and object instant retrieval. So you are going further and further away from the original task. And what are these vertical lines or vertical bars? This is the best previously reported state of the art. The green ones, CNN features off the shelf, is this paper. Sometimes it is better, sometimes it is worse, but it is competitive to doing all of this hard work. And then you can have CNN off the shelf features plus some data augmentation, and you can get a little bit of boost out of data augmentation. And there are also some specialized CNN architectures for these tasks. And because they are specialized, they are most of the time gonna do the best, but still, we are having a very good baseline, taking an image, pushing it through a CNN and getting some features, and then feeding it to a support vector machine or a logistic regression. So let's start with image classification. But what we are doing now is changing the data set. Rather than ImageNet, we are using Pascal VOC, and the task is also slightly different. In each image, you could have multiple categories. That's why accuracy is no more a good metric, and you're going to use average precision per category or mean average precision for the entire categories. I'm going to tell you about the details of the mathematical formulation of average precision later on when we do object detection. But for now, it is worth noticing that the task is slightly different. There could be multiple objects in one image. And the CNN support vector machine with the augmentation is doing best on almost all of the categories except a few. And in total, that's doing the best. So that's this part, object classification. You can have indoor scene classification. So indoor scenes are important for robots. And let's see, again, the CNN SVM with augmentation is doing the best. And let's take a look at the confusion matrix. The algorithm, these features are confusing a bakery with a buffet, a cinema with an auditorium, and a library with a bookstore. So even the mistakes are not that bad. And as I said, CNN aug stands for you have some data augmentation going on, like cropping and rotating your samples. For bird subcategories, we saw this in the previous paper also. We are seeing it help here as well. DCAF is the previous paper. And these augmented CNNs are doing as good. These ones were using part information. This one is not. What else? You can have human attributes. This is the next task. And the attributes are whether you're dealing with a male or whether that person has a long hair, whether they have glasses, hat. So these are really different from what we saw in ImageNet, which was categories of airplane, cat, dog, etc. This is totally different. Is this person wearing a t-shirt? Do they have long sleeves? Are they wearing shorts, jeans, long pants, etc.? And the last one is object retrieval. For object retrieval, you take two objects, push them through your neural network, you take the features, you compare the L2 distance between the features, and that's going to give you a measure of closeness between two images. Now that you can compare two images, you can compare one image to an entire data set. So what is the task? you want to do search, but you don't know how to describe your search, but you have an image. You want to bring up all of the images that are similar to the image that you have at your hand. That's going to be called object retrieval. And you have different data sets for it: Oxford 5K, Paris 6K, sculptures, and etc. These are hand engineered features, and CNN features are doing pretty good. So these features are transferable.
Where were the features learned from originally for all of these cases?
What do you mean?
Is it like last time where you did a big training on AlexNet, or you did a big training, excuse me, on ImageNet, and then fixed all those weights and then used it as a feature generating network for some other data set?
Yes, it's exactly the same thing.
And so what is the source data set?
ImageNet.
Okay.
Actually, ImageNet is going to be what we are going to use for transfer learning.
And what is the objective function then? In the original one, is it still just image classification on ImageNet?
Yes, so that's the objective.
Okay.
So you learn your features from object image classification using ImageNet. That's going to give you your CNN, and that's going to be your feature extractor.
Yeah. And then you use those features to do all these other things. Okay.
Exactly. And this was without any fine tuning of the original CNN. You can also free up some of these parameters to be learned, to be fine tuned. That one is also transfer learning. Like here, you can have a lock on them, or you can release the lock and let those weights be trained. And we know that if you let it fine tune, you're going to get a boost in terms of performance, maybe even better than training on the original data set. Any questions?